So start streaming, that's all good. Okay. All right, so we are back to binary number comparison. And instead of kind of skipping through a bunch of stuff, because last time I did skip through some of the proofs, so what we'll do today is kind of go through the proofs, because as we go through the proofs, it will become clear how the borrow flag works, okay, and why it works. All right. So we'll just kind of be, I'll just be looking at certain portions of this note, which is accessible from Canvas. Do we have any issues with these two statements? 0 is less than 1 is true, 1 is less than 0 is false. Can we establish that? Okay, very good. So the next thing I want to do is to say, if n is a positive integer, which means it starts with 1, then I'm going to say that this condition is always true. Okay? So 2 to the power of n is always greater than the summation of I going from 0 to n minus 1, 2 to the power of I. In other words, if you plug in actual values, okay, when n equals to 3, 2 to the power of 0, which is 1, plus 2 to the power of 1, which is 2, plus 2 to the power of 2, which is 4, 1 plus 2 plus 4 is 7, and 7 is less than 8. Okay, so it definitely works for the case when n equals to 3. And you can probably check and say, oh, it works for when it also works when n equals to 4, when n equals to 5, and so on. But is that a proof? Is that telling you that no matter how large n gets, this property still works? It is not a proof, okay? Because all I did is to give you a few samples and say, okay, this particular statement seems to be true, all the time, because it is true for all the numbers that we can choose. But it's always possible that you can choose the next number and it doesn't work. Is that okay? Well, okay, 2 questions. Does everybody understand the concern that the next number, if I pick n to be 371, it suddenly doesn't work, okay? Because there's nothing that assures us that it always works. So that is the concern. So how do we make sure that this statement is always true? In mathematics, what do you use?
Infinitive. Infinitive.
Not infinity. What is the technique that can basically, say, okay, after this, we know for sure that this statement is always true. It's a proof. Okay, we want to go through a mathematical proof to convince ourselves that that is always true for any n that is greater than
Induction.
Sorry?
Induction.
And we can use proof by induction. Yes. Okay. So this class is not CISP 440. Okay, which focuses on proofs, techniques, and logic and stuff like that. So that means, I'm not going to quiz you guys on proof techniques, but I still want to go through the proof just so that, you guys have some exposure to proof by induction, and also, so that you are all convinced that this theorem is always true. All right? So does everybody understand, where we are heading right now? Okay. So proof by induction is kind of interesting because it separates the proof into 2 very distinct steps. The first step is what we call a base case. A base case is you have to find a particular value, a concrete particular value for n, and then you show that it works. Okay, the theorem is in fact true when n equals to this specific value. Is that okay? And most of the time you choose a value of n that is at one end of the range of numbers. Okay? But since we're talking about n being a non-zero, non-negative, positive integer, when n equals to 1, that's one end of the whole range where the theorem is supposed to work. So we choose n equals to 1 and see what happens. When n equals 1, then we can spell out the actual statement and say on the left-hand side we have 2 to the power of 1 because n equals to 1. On the right-hand side, we say, oh, that's only one term because when n equals to 1, I only goes from 0 to 0. Because it only goes from 0 to n minus 1. When n itself is 1, n minus 1 becomes 0. And so the only term we have to worry about in the sigma notation is 2 to the power of 0, which is 1. So then you look at 2 to the power of 1, which is 2. You look at 2 to the power of 0, which is 1. And now we can say, well, at least the theorem works when n equals to 1. Is that okay? But that's only the first part of a proof by induction. So the second step of a proof by induction is called the induction step. So the induction step is kind of confusing in a way, but intuitively it makes sense as well. In the induction step, it has two parts. Okay, I wouldn't call it two steps, but it has two parts. The first part is an assumption. Okay, so the assumption in this case is, let's just say that the theorem works all the way up to some k value. When n equals to k for some k, it's fine. It works. But that's only an assumption. But we don't question that assumption. We just say that, let's just say the theorem works all the way up to the case when n equals to k. The question now is, can we prove the theorem is true when n equals to k plus 1? The next step. So using the assumption, can we say we can now bridge it to the next step? That okay? So the actual proof in this case, in terms of algebra, is fairly easy. Can someone tell me how I got from the first step to the second step?
Identity.
Not identity. It has to do with it is a trick in exponents.
Yeah,
yep.
exponents.
Yep, exactly. Because 2 to the power of k plus 1 as a whole is 2 times 2 to the power of k. Right? But 2 times whatever is just that thing plus itself. So that's what I did to expand it to 2 to the power of k plus 2 to the power of k. Are we good with that?
Mm-hmm.
Okay. And how did I get from the second step to the third step? Going from here to here. Subtraction. What did I subtract from both sides?
2 to the power of k.
2 to the power of k. On the left-hand side, it is really obvious, right? One just disappeared. What about on the right-hand side? It's a little bit more subtle. Because in the second step, I still had I going from 0 to k. But as the last step, I had it back to I equal to 0 to k minus 1. Hold on a second. We already made the assumption that that is true, didn't we? That's the end of the proof. Is that okay? Yep.
Wait, sorry, so how is 2 to the power of k equal to k minus 1? Or sorry, 2, never mind.
You changed 2 steps.
Sorry, when you moved it over. Actually, okay.
Okay, all right. So this is the end of the entire proof by induction. Okay. So are you guys okay with this concept, or are you going like, well, I'm not really sure that this actually works? Do you want an analogy to kind of help you remember how this works?
Yeah.
Okay. So let's say that's a cruise ship over there. This is the ocean, and I want to get over there. Is that okay? And the idea is there are sea turtles along the way, and I'm hoping that I can just walk on the back of sea turtles and eventually get to the cruise ship. Okay? So the first thing I need to prove is I'm not sinking right now. I'm not drowned already. All right? So I'll just say that I'm standing on an island. That's your base case. Your base case is simply saying that yes, you're on something, you're not drowning, you're standing. Is that okay? What about the induction step? The induction step is basically saying assuming you're already on the back of a turtle. Okay? Can you prove that there's always another turtle in the direction of the cruise ship that is only one step ahead of you? That is the induction step. So if you can prove the induction step, that means no matter which turtle you're on, there's always the next turtle that is one step closer to the cruise ship and is only within a step distance from the turtle that you're on. Is that okay? So how did I get onto the turtles? Well, you're on the island, which quote unquote is a turtle, is a big, huge, gigantic turtle. And then you just go, then you have proof that you can eventually get to the cruise ship. Is that okay? More or less? Okay. I know that most of you would just remember the sea turtles, but not how it is related to mathematical proofs. You just walk away with that picture in your mind, tag on a tropical island, cruise ship, and sea turtles. For some of you, you might even imagine, oh, there's the Little Mermaid. And okay, so moving on. Okay, so the next part is a proof, and this part is a little bit more difficult to understand. So we first have to talk about the terminology. So once again, we have two numbers. Okay, we have x and y as the numbers that we're dealing with. And this time, I'm just going to say that we are using up to m bits. We're using exactly m bits to represent values with these two binary numbers, x and y. And we'll also assume, okay, because it's a fixed width integer, we'll just go ahead and assume all the leading zeros are all the leading digits are zeros. All the more significant digits are zeros. Is that okay? In other words, you are dealing with, let's say you're dealing with 32-bit numbers when n equals to 32. So we'll just say that, bit 32 is a 0, bit 33 is a 0, bit 34 is a 0. We just assume that all the digits to the left-hand side of the most significant digit are zeros for both numbers. That seems to make sense, right? Okay. Because usually we don't write the leading zeros. So this part we can just kind of ignore. So this is the first statement that is actually very important. So we are going to start with m. Okay, so we start with m minus 1, we start with the most significant bit. And then we're trying to walk our way backwards to the less significant bits. In other words, when you look at a number, we're starting all the way from the left-hand side, and we're trying to walk to the right-hand side, looking for bits that are different. Okay? So we keep going backwards until we find p, okay? So that bit p is the first bit or the most significant bit that shows a difference. Is that part okay? So bit p is the first bit, is the most significant bit so that your p, x, and y are different. All the bits that are more significant than bit p are the same. Is that okay? Does everybody understand what p is representing? It is the position of the bit where we encounter the first difference of the two numbers. Okay? All right? Well, if they're different, there are only two ways they can be different because we're talking about binary numbers. Okay? So one way they're different is x has a digit of 0, y has a digit of 1. And then the second way they can be different is when x has a value of 1 and y has a value of 0. Do we agree? Can we agree that there are only two ways that two bits can be different? Okay? All right. So we'll look at each situation and say, okay, what's going to happen when we have, let's say the first case, when xp has a value of 0 and yp has a value of 1. Can we make any conclusions? All the other bits to the left-hand side are the same. Okay? This is the first bit, the most significant bit that shows a difference. And we know, okay, that x has a value of 0 and y has a value of 1. What can we conclude?
Y is bigger.
Y is bigger. X is less than y. Okay. Do we need to look at the other bits? Do we have to look at all the bits that are less significant than bit position p? Why not?
Because it's
No, well, okay, technically speaking, this one is representing 2 to the power of p, right? So, but we have already proven that even if x has all the less significant bits being 1, it cannot exceed the value of this one. Where did we talk about that?
And the induction proof 2 to the k.
Exactly. So that theorem enables us to make this conclusion and say, okay, we do not need to look at any less significant bits. Are we making that connection? More or less? Okay. Okay, so that handles one case. What about the second case when x has a value of 1 and y has a value of 0? Then x is less than y is false. Okay. We also know that x is actually greater than y, but we don't care, okay? Because we only need to know whether the minuend is less than the subtrahend. That's the only thing we need to know. Now, if you go all the way to p equal to 0, and we still cannot find 2 bits that are different, then the two numbers are exactly the same, which also means x is less than y is false. Okay? So is that all making sense? All right? All right. This is all great, okay? But it doesn't help us in the sense of, well, we got a subtractor, okay? We know how to do it really fast using the look ahead mechanism, and we have a final borrow bit. This doesn't tell us how we can use that circuitry to determine whether the minuend is less than the subtrahend. Does that make any sense? It only tells us manually how we can tell whether a number is less than another number or not, but it doesn't tell you how to use circuitry that we have already built to do it. So we want to be able to reuse the circuitry that we already have in order to tell whether the minuend is less than the subtrahend. So somehow we have to take this and go like, okay, this is all good, but we're going to have to link what this is talking about to circuitries that we have already talked about. Okay. So the next step here is to introduce a little bit of notation. I don't think the notation is actually used anyway in here, so we'll just ignore that. But this is what we actually want to, this is what we want. So let's see if we can figure out what this is really saying. So over here, I'm just defining v as a function, because x is a binary bit pattern. Okay, a binary bit pattern really doesn't have any intrinsic value that it's representing. It really is just a bunch of zeros and ones. Okay, so by using v of x, I am basically saying we are not looking at the binary bit pattern itself. We're looking at the value represented by x. Is that okay? And this is the value represented by y. So we are now trying to say the value represented by binary bit pattern x is less than the value of represented by the binary pattern y if and only if, okay, the double-sided arrow here is if and only if Tm equals to 1. What is Tm? What does T stand for in a binary subtraction according to the earlier modules that we have already explored? Did anyone read the binary subtraction thing?
It was like the carryover for the subtraction.
It's the borrow, exactly. It's the last borrow. It's the borrow from the most significant digit at the very end. Okay, that's borrow out. So what this is saying is, I'm claiming that the borrow out from a subtractor is a 1 if and only if the minuend is less than the subtrahend. That is awfully handy, isn't it? Okay, because we already have that circuitry. And some of you may say, but we only got the circuitry for adders. What is the difference between an adder and a subtractor? In a carry look ahead adder, what do you need to tweak to make it a subtractor? Negation. Where do we apply the negation? You got it. Just keep going. It's okay. We negate the x. Okay? So when we compute the g, we negate the x. We keep the conjunction, we keep the y, we just have to negate the x first. When we compute the p, we also do the same thing, we negate the x. So if you just negate the x for those two gates, it becomes a subtractor. If I give you the circuitry of a carry look-ahead adder using the multi-bit representation, it will take you 2 little changes to turn it into a subtractor. Okay? Alright, so that means we have the circuitry already for a subtractor, and we are using the last borrow of a subtractor as an indicator of whether the minuend is less than the subtrahend. This is just what I claim, okay? I am claiming that this works all the time. But the question is, does it really work? So now we need to prove that this works. So the first thing we do is we take a look at this equation here. Does that look familiar to you? I don't want to hear no, but if that is the honest answer, then I cannot, that's not much I can do about it. You can do something about it. Where have we seen this before?
The carry look-ahead.
Subtractor. When we talk about binary subtraction, this does not even have anything to do with borrow look-ahead. This is how we define the borrow of digit I+1 using the borrow of xi minus yi, or the borrow of qi minus ti. It's coming from the binary subtraction module. Okay, so this I'm just copying and pasting into here. All right. So how do we fit this into the recursive algorithm that we have talked about a little bit earlier? So now we just keep the same assumption. We will still say the same thing about p. P is the bit position where it is the most significant bit that is different between the two binary numbers. So same idea for p as a position. And we have two cases, just like last time. So the first case is, what if xp is a 0 and yp is a 1? In other words, the most significant bit that is different between x and y, x is the one that has a 0, y is the one that has a 1. How is this going to impact the carry of bit position p plus 1? That is the question. Okay? So what we do is we plug in the values. Okay? xp goes here, yp goes here. If I know x and y, do we know what is q? What is qp? Q is the intermediate difference in this case, but it is the same thing as an intermediate sum because it is the result of exclusive OR. Okay? So if we know that xp is a 0, yp is a 1, what is the exclusive OR between these two? 1. So that means qp is guaranteed to be a 1. Is that okay so far? So when you look at p plus 1, we know that it will look like this because we can fill in the blanks. Okay? xp goes here, yp goes here, and then qp, which is the exclusive OR between x and y, goes here. The only one thing I don't know is what is ti. But I don't need to know. Why do I need to know qi? I mean ti over here, or tp in this case. Well, it's because b, the borrow of 0 minus 1 is, do you guys remember the subtraction table?
Should be 1.
It's a 1. And this is an OR operation. Okay, I don't need to know the rest. Because true or whatever is always true. So this part is already guaranteeing that p plus 1 is a 1. Is that okay? The next point is kind of confusing. Let's see, did I say that here? X is less than y is true due to the corollary that we have proven earlier. So it doesn't really quite say the rest, okay? Which is, well, we have just determined what is t p plus 1. What about t p plus 2 and all the more significant borrows? What do you think? how would this, knowing that t p plus 1 is 1, impact the other borrowed bits to the more significant side? Well, let's plug it in. Okay, so I'm going to use my tablet to show this part here. Is this part of the class reminding you of a math class instead of a computer science class?
So class has been basically discrete math course. Less or more.
Yeah, but so the question is it reminding you of a math class instead of a computer science class? No? Okay. Well, if you guys say yes, I was about to ask, should there be a difference between a math class and a computer science class?
No.
Yep. And why not?
It's a bit applied math, yeah.
It is applied math. That is correct. Computer science is a branch of mathematics. Not everyone likes that view, but it is true and nonetheless. Hmm?
Those people are stupid.
Well, I wouldn't say, stupid, but they do not see mathematics and computer science to be related.
Everything. Just like saying chemistry is not a branch of physics. It's everything stems from that. Except logic.
Well, natural sciences are not based on math. They utilize math as a tool, but they're not,
But they're based off chemistry. They're based off biology, which is based off chemistry, which is based off physics, which is based off mathematics.
There is certainly a truth to that statement. However, at a macro scale, it doesn't work, like that. So in chemistry, if you keep looking at molecules in regular chemistry instead of molecular chemistry, then you can no longer look at animals as species and how they evolve and stuff like that. So you kind of have to take a step back and look at the kind of macro vision instead of the micro vision. Okay. All right. So let's see here. We can now look at the tablet screen. Okay, where's my? Okay, that's not it. Where's my tablet screen? I made a connection already. Maybe not. It's supposed to tell me that it is making a connection, but it's not making a connection yet. Did we start? Yeah.
Is it the one on to your right? Look, there's another Biz Advisor tab in the right one.
This one?
No, three more.
These two?
After that. Can you click that?
That's just the virtual screen itself. It has found it. Okay, well, if all fails, disconnect.
Oh, error occurred.
Yeah, because I just disconnected it. And let's see. One more time. Okay. Okay, there we go. Okay, so remember what we're trying to figure out is t plus 2. Okay. So is this part okay? Is everybody buying that t plus 1 is a 1 in this particular situation? Okay. Okay. So let me see if I can do this. Okay, I will show a part of this screen here, and then we'll. Okay, I can't adjust the scrolling very well. There we go. Okay, and now we take a look at the tablet in a way that to show both at the same time. There we go. Okay. All right. So we already know that p plus 1 is a 1. Are we good so far? Because we are handling the case when xp is 0, yp is a 1. Is that okay? All right. So our job now is to figure out what is t subscript p plus 2. Is that okay? So we'll go with the definition first. So the definition of t p plus 2 is b x p plus 2 y p plus 2 or b of q p plus 2 comma t oops, I take it back. Okay, I got these, all of these should be ones because we are all prime. Okay, these are all p plus ones. Okay. My bad. Okay. So except for the p, on the left hand side, which has a subscript of p plus 2, all of the other subscripts are p plus 1. Is that okay? So that's the definition of the borrow flag. Okay, is it can be one, but from two sources. It can be coming from the subtraction of the numbers that are given to you, but it can also be coming from the subtraction between the partial difference and the borrow of that column. So are we still okay so far with this? Yes? Okay. So now the question is, what do we know about xp plus 1, yp plus 1? What do we know about these two terms up to this point? What was the assumption again? What is significant about p? It is the most significant bit that is different between x and y. Okay? So if position p is the most significant position that is different, what happens to all the places that are more significant than p? X and y are the same. Okay? All of those other bits are the same. So if x p plus 1 and y p plus 1 are the same, they can both be 0, they can both be 1s. Do I really care when I'm trying to evaluate the borrow function? Because all of these, they're guaranteed to evaluate to what? Do we have a borrow? Do you have a borrow when you subtract 0 from 0? No. Do you have a borrow of 1 when you subtract 1 from 1? No. Okay, so this part is guaranteed to be a false. False or whatever is whatever. Okay, so now the key is to look at this one here. When x and y are the same, when xp plus 1 and yp plus 1 are the same, what is the q term corresponding to it? What is the exclusive OR between x and y when x is 0 and y is 0? Or when x is 1 but y is 1? They are the same. What is the exclusive OR? 0. Okay, very good. So we know that qp plus 1 is guaranteed to be a 0. All right. Only one more term that we need to kind of look into. What about p plus 1? What about this term over here? We just determined that it's a 1, didn't we? All right. Well, that's a 1. So what is the borrow of 0 minus 1? It's a 1. So this entire side is a 1. And then we just look at this is false or true. And what is that telling you? The whole thing is true. Great, Tech, you just used 10 minutes to show that p plus 2 is true. What about p plus 3? Are we going to spend another 10 minutes to do this? So if you apply this and keep going to the more significant side, at some point you're going to hit Tm, because m is the number of bits of this number. So when you hit Tm, what you're really saying is Tm is guaranteed to be a 1. Is that okay? Which is exactly what we are trying to achieve. We are trying to prove that when Tm equals to 1, x is less than y. Are we doing okay so far with this proof? Okay. How many of you need to take cisp 440? Okay. So this is a preview of what you'll be seeing in cisp 440 if I am teaching that class. and I do teach that class here exclusively. Which means if you want to stay at AR, there's no way to avoid having me as your professor for CISP 440. But I also heard that class is offered online in some of the other colleges. Okay, so the other one is what happens when xp is a 1 and yp is a 0. Okay, because that's the other way for the bits to be different. Okay, so in this case, using very similar reasoning, we can guarantee that tp plus 1 is a 0. But using also very similar reasoning, we can also show that tp plus 2 is also a 0. And using very similar reasoning, we can propagate that all the way back to tm, so that tm is a 0. Okay. If you cannot find anything that is different, then the two numbers are in fact the same, and as a result, the borrow flag is going to be a 0. Okay, so that's also done. So when we are done with all of these steps, we should be convinced that Tm is a 1 if and only if x is less than y. Interpreted unsigned. So are we convinced so far? Okay. So once again, this class is not about proof techniques, so I will not quiz you on proof techniques. But it is still important, I think, important for me to show you step by step how do we know that the borrow flag alone can indicate that the minuend is less than the subtrahend. All right? Cool. So now we look at sign interpretation. Now, when we talk about sign interpretation, let's just take a look at this notation here. Okay? So once again, we're using M to denote how many bits we are choosing to use for our representation. So V of x, once again, is the value represented by the bit pattern x. But this time, the value that is represented involves an expression that is what kind of operator is this again in C and C++? The question mark and the colon? Ternary operator. It's called a ternary operator. Okay? And what does it do?
If then else.
It's an if then else. Okay? The first part to the left of the question mark is the condition. If the condition is true, then the second part, which is the part between the question mark and the colon, is evaluated and returned as the actual value of the entire ternary operator. If the first part, which is the condition, is false, then we only evaluate the third part, which is the part to the right-hand side of the colon. And whatever the value of that thing is, becomes the value of the ternary operator itself. So is that okay? Does everybody understand what a ternary operator is? Or reminded of what it is? Did you guys talk about that in CISP 360? But do you know it now? Yeah. Okay. Alright, so the value represented by bit pattern x depends on whether the most significant bit is a 0 or 1. Okay? If the most significant bit is a 1, then we know we are representing a negative value. Okay? But how negative of a value are we looking at? So now we look at this part here. So there's a negation on the outside here, and there's this operation in the inside. So let's forget about this part and only focus on the summation here. So let's focus on just the sigma notation. So in this particular sigma notation, it is off by 1. It is actually off by 1 thing. No, it's not off by 1. Okay, never mind. Okay, do you guys still remember what is 2's complement? Okay, what is 2 complement? Is 1 plus 1's complement, which is 1's complement is also known as bitwise not. Okay, but what was the reason to implement 2's complement? Why did we have to do a 1 plus and then a bitwise not or something?
So to express a value that was greater than the bits that we had.
Exactly. So when we have 4 bits, okay, let me go back to the tablet. So when we're talking about 4 bits, okay, so let me scroll this a little bit, okay. So when we're talking about 4 bits, when m equals to 4, okay, 2's complement is trying to do this, okay. If x is the bit pattern, 2's complement is trying to do this. That is what it's trying to do. You guys remember that? Because that will help us find out what is the negation or the arithmetic negation of x. Is that okay? Alright, so getting back to the notes here, what do you think this part is? The same thing, okay? This is actually doing 2's complement. But 2's complement will give you the flip side. In other words, if x is a negative value, this will give you a positive value, the mirror image of the negative value. And that's why I did the final negation on the outside to flip the sign back to what the value is really representing. Is that okay? No? Yes? Maybe? Okay. Alright. But when x subscript m minus 1, when the sign bit is a 0, I don't have to worry about a single thing. We just add up all the powers of 2 that are relevant, and we're done with the value. Is that making any sense? So when you look at each term of the sigma, I'm multiplying 2 to the power of I to x subscript I. X subscript I, once again, what do you think it is representing? We have been using this notation for quite a few weeks, well, 2 weeks already. So x subscript I is representing bit I of x. Okay, very good. Which represents the quantity of 2 to the power of I. So when you add up all those terms, it will be quote unquote the value represented by the binary number. Yeah, alright? Okay. How did I go from the first line to the second line? What got changed? So let me move it up a little bit. So what got changed between the first and the second line?
You just distributed the negative?
Yep, exactly. So what I did was something that doesn't seem to be very important. Because there's a negation on the outside, I applied the negation to whatever is in the inside. In other words, I distributed the arithmetic negation. But by doing that, this 2 to the power of m becomes a negative quantity. And then whatever was negative to begin with, which is the entire sigma, because of double negation, it becomes positive. And then I just exchange the position, because most of the time we like to express something as blah 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 minus blah blah blah. So that's how we change from this expression to this expression here. Is that okay? So it's really just kind of algebra, with this one. What happened between the second line and the third line? What did I do? I did several things, okay? I did something with the middle term or the second term of the ternary operator or ternary expression. I also did something to the third one, okay? So let's see what I did with each one and whether we can say that makes sense or not. Okay, so we'll deal with this part first. We'll deal with this transition to this over here. What did I do? Okay, the first thing you might notice is the sigma is tweaked, right? Because in the original form, I'm going from 0 to m minus 1, but now it's only going from 0 to m minus 2. So I lost, quote unquote, I lost one term. What did I put that term?
You pulled it out and put it with the numbers.
Exactly, I pulled that term and I put it here. But it becomes a subtraction, how? It's an addition here, right? But because there's a subtraction here to begin with, so if I negate it over here, it becomes a positive or addition here. Okay. I did something on this side too. I also lost the term for I equals to n minus 1. But this time there's no compensation and say that, oh, I just moved it over here. No, I just got rid of it. Can I do that? When do we evaluate the third item of a ternary operator? When the condition is false. When the condition is false, we evaluate the third part of a ternary expression. And which term did I lose?
X n minus one.
Times 2 to the power of n minus 1. But if x subscript n minus 1 is a 0, that term is going to be 0 anyway, so I can just get rid of it. Is that okay? Alright? So are we okay, comfortable with the second to the third line? Okay? What about the third line to the fourth line? Yeah, what did I change? Okay, let's look at the middle term first, the second term of the ternary expression. What did I do to go from this part to this part? I didn't do anything with the sigma anymore, okay? The sigma stayed the same. So what I did is I say 2 to the power of m minus x subscript n minus 1 times 2 to the power of n minus 1 is now reduced to just x subscript n minus 1 times 2 to the power of n minus 1. How can I do that? It relies on the fact that this is the second expression of a ternary operator. When do I evaluate the second expression of a ternary operator? When the condition is true, right? In other words, when I evaluate this, I know x subscript n minus 1 is a 1. Is that okay? Which basically means you can just kind of pretend that it wasn't here, because it's just 1. Is that okay? So if I pretend that x subscript n minus 1 is not even here, does this make sense? It makes sense because 2 to the power of m is 2 times 2 to the power of n minus 1. You take 1 away, you have 1 left. But I choose to re-express, I choose to kind of use x subscript n minus 1 here, which really doesn't matter, right? Because x subscript n minus 1 is just 1. 1 times whatever is always whatever. Is that okay? And on this side, I chose to reintroduce that term, which doesn't also matter because n subscript n minus 1, when we evaluate the third expression, is basically saying, oh, we know it is a 0 already. So I can always say, oh, we can just introduce whatever, we can always say subtract 0 from something, right? But since x subscript n minus 1 is 0, whatever I multiply it to, the whole product is going to be a 0. So I can always just plug this back in. Is that okay? But why would I do something like that? Why would I reintroduce a term that disappeared earlier? What is the rationale of doing it?
To eliminate the conditional statement or ternary statement.
Exactly. I don't need a ternary operation anymore. I don't need a ternary operator. Because when you look at the second item, other than the additional unnecessary parentheses, does it look the same as the third one? It's exactly like the third one. The second term and the third term are exactly the same. Which basically means I don't need a ternary operator anymore. Throw that away. So now I have a unified expression to handle the value of x, to express the value represented by a binary bit pattern x. Are we good so far? Okay? But when you look at this, okay, why do you think x subscript n minus 1, which is the most significant bit of a signed number, why do you think it's called a signed bit? How does this quantity relate to this quantity over here, assuming x subscript n minus 1 is a 1? If I just give you one fact, okay, if I just tell you that x subscript n minus 1 is a 1, okay, what do I know about the relationship between the whole sigma and just this part here?
The value we're subtracting is greater than the summation over there.
And as a result, the difference is negative. And that's why it's called a sign bit, because this alone, x subscript n minus 1 alone, determines whether the value that we are representing is negative or not. But this makes it clear, okay? But you also have to remember, this is only guaranteed because of the theorem that we proved earlier, that this term all by itself, 2 to the power of n minus 1, is greater than this entire sigma. It doesn't matter, what the less significant digits are. Even if they're all ones, it cannot catch up with 2 to the power of n minus 1. So is all that stuff okay? Okay. So now I'm going to use this derivation here, and you guys can tell me whether it makes sense or not. X is less than y if and only if x minus y is less than y minus 1. I'm subtracting y from both sides of the comparison. Is that okay?
Yeah.
Nobody has any objection to this? Okay.
It's balanced.
It's balanced, exactly. So going from the second line to the third line out again, everything is kind of shifted because I formatted this incorrectly. But if you look at the meaning of the expression, can I say y minus y is a 0? Okay, cool, right? But what is the bottom line? Pine needles. What is the pine tree? The pine tree is if x is less than y, x minus y is less than 0. Now, how come we didn't use this before in the other section? Because in the other section, we're dealing with unsigned values. Even the difference is unsigned. We cannot say, oh, is it negative? No. They're all non-negative values. Okay, so with that one, we only have to rely on the moral flag. But with signed values, hey, we can use the sign bit. We can carry out the actual subtraction, look at the sign bit of the difference. If the sign bit of the difference is a 1, which means the difference is negative, then we can conclude that x is less than y. That would be too easy. Okay? But that's a good start. Okay? It's a very good start to basically say, it kind of makes sense that we can just look at the sign bit of the difference and use that to tell us whether the minuend is less than the subtrahend or not. Okay? But if this is going to work, then this entire module would have ended here. There's more stuff coming, after this. Why? Why is this adventure not ending yet?
What happens when we run out of places?
Well, exactly. What if the difference cannot be represented given the bits that you have? What do we mean? Okay. So we'll go ahead and take a look at these examples. There are 4-bit subtractions. Okay. 6 minus 3 is non-negative. 6 is not less than 3. We good. Negative 1 minus negative 2 is non-negative. Negative 1 is not less than negative 2. In other words, I'm carrying out the subtraction and then use the difference, the sign of the difference, to tell us the ordering of the minuend and the subtrahend. 3 minus 4 is negative because it's negative 1. As a result, because the difference is less than 0, we can conclude that 3 is less than 4. Negative 4 minus negative 1 is negative, so negative 1 is less than negative 4 is less than negative 1. Okay, cool. And then I stop saying something, at that point. Okay? What is negative 4 minus 5? And remember, we're dealing with 4-bit examples.
So it should be negative because negative 4 is less than 5.
It should have been negative 9, but it's not. Because with 4-bit representation, the most negative value that you can represent is negative 8. Negative 9 is out of that range already. Okay, well, if negative 9 is out of the range, what does it look like when we carry out this subtraction? Well, let's do that on the side. Okay, this is negative 4 minus 5. Okay, so we'll use the tablet to do it. Negative 4 minus 5. But I don't want to do it using base 10. I want to do it in base 2 because we want to look at the difference in base 2 and limiting only to 4-bit subtractions. Okay? How do we represent negative 4? What does it look like? 1, 1, 0, 0. Very good. Okay. Did you guys remember that, or did you look at the number wheel?
Super genius.
Okay, so -4 is represented by the bit pattern of 1, 1, 0, 0. Okay, so to know why that is the case, there are several ways. Okay, so I'm just telling you guys how to do it. You can look at the representation of 4, apply 2's complement to it, you will end up with 1, 1, 0, 0. That's one way. You can look up the number wheel, okay, and look up, okay, what is -4 on the number wheel? It is next to the binary pattern of 1, 1, 0, 0. That's the other way. The most tedious way is to remember is 0, okay? If you go counterclockwise, we got 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0. That's -4. So there are many ways to kind of visualize how -4 is represented by a Formy number of 1, 1, 0, 0. Okay? You have to pick the one that works well with you. Okay? But it is important to understand how to do it. Okay. So -5, okay, 5 is non-negative, so that is an easy one to deal with. 0, 1, 0, 1 in base 2. So we'll just go ahead and carry out the subtraction here. 0 minus 1, so I'm going to do a full subtraction here. 0 minus 1 is a 1 with a borrow. There's an implicit 0 here because this is not the second step of some bigger subtraction. So 1 minus 0 is a 1. So we put a 1 here. Alright? And then we have 0 minus 0. Okay, let me use this pointer to emphasize where we are at. 0 minus 0 is a 0. So we put a 0 here. And then 0 minus 1 is a 1 with a borrow of 1. There we go. Then we have 1 minus 1, which is 0. And then we have 0 minus 1, which is 1 with a borrow of 1. And then over here, we got 1 minus 0, which is 1. And then we have 1 minus 1, which is 0, with an overall borrow of 0, which is not important in this case. Because what we're trying to do is to look at this sign here. So when we look at the sign bit of the difference, it is a 0, suggesting that the difference is non-negative. Okay, because we just talked about a little bit earlier how the sign bit determines the sign of a number in sign representation. In fact, this is saying it is 7. That doesn't make sense to me, right? -4 minus 5 is 7. I would flunk out of a math class if I said that in a math class. But in a computer science class, I can say that with the qualification of we're doing 4-bit calculations. Okay? So in a math class, you can still claim that, but then you have to say we're doing modulo 16. Okay? If you say that we're doing modulo 16 math, your math professor will still say, yep, it's okay. But we have a problem, don't we? Because earlier, okay, my claim, okay, if I go back to the discussion, my claim is if the difference of x and y is less than 0, x is less than y. If and only if. Okay, that's a very strong statement. But now we have a counterexample to show that, oops, that's not going to work. It is not going to work because we have just overflown the Formy number. We're trying to represent something that we cannot represent given the number of bits that we have. Okay? So one way to look at this is to say the sign bit is lying. Okay? So let's combine the fact that the sign bit is saying it is a 0 and it is lying. What is the actual true sign bit? How many ways can the sign bit lie? It's a binary number. It can only lie one way, right? Which is opposite to what it is supposed to be. So if the sign bit says, oh, the sign is a 0, and then the next guy says, nope, he's lying, what is the actual answer? The sign bit is a 1. Okay. Cool. So understanding why the sign bit doesn't work in some cases. When the difference is overflowing, the sign bit is going to lie. Is that okay? So that means we need a way to tell whether the sign bit is lying or not. That turns out not to be very difficult, because what we need to do is to evaluate these are the two ways that the sign bit can lie. Okay? So once again, x is the minuend, y is the subtrahend, and d is the difference. Okay? If you get into one of these two situations, you can say the sign bit is lying. Well, let's think about it. X is the minuend, y is the subtrahend. So we are trying to calculate x minus y. X is negative, y is non-negative. Somehow x minus y in a 4-bit calculation or whatever fixed width you're dealing with is non-negative. Does it make sense to you that the difference is non-negative when you start with a negative number and you're subtracting a non-negative value from it? Does not make sense. Okay? So this is one way the sign bit can lie. Next one, flip everything. In terms of the sign, you start with a non-negative value, you subtract a negative value from the non-negative value, and the difference somehow is negative. Does not make sense at all. But once again, the sign bit is lying. Are we doing okay so far with these two statements, which basically states, when is the sign bit lying? Is that okay? All right. But this is not using bit operations and whatnot. This is using arithmetic operations that we can do, but the computer cannot do that. Okay? Okay, so let's look at each one and say, can we look at individual bits to see whether x is less than 0 or not? Which bit do we look at so that we know that x, the minuend, is less than 0?
The MSB.
The MSB, also known as the sign bit. Okay? So we can look at the sign bit of x. If the sign bit of x is 1, we know x is less than 0. Yes? We had that conclusion way earlier. Okay? The second one concerns y. How do we know y is greater than or equal to 0? The sign bit is a 0. How do we know that the difference is greater than or equal to 0? The sign bit is a 0. Oh, so that means if the sign of x is 1, and the sign of y is 0, and the sign of the difference is 0, the sign bit is lying. The sign bit of the difference is lying. Well, that's how we end up with this expression here. X subscript n minus 1 is the most significant bit of x, which is also the sign bit. This is negation. Negation applies only to the item immediately to its right-hand side. So this is basically the negation of y subscript n minus 1, which is the most significant bit of y, which tells us whether y is negative or not. Okay? When y is non-negative, that bit is going to be a 0, but in order to flip it into a 1 so the conjunction can become a 1, I have to negate it. Same thing applies to d subscript n minus 1. It is the sign bit of the difference. If the difference is non-negative, the most significant bit of the difference is going to be a 0. But I need to flip it because I want this entire conjunction to be a 1. So that the overflow flag can basically be affirmed, can affirm that we have an overflow situation. Is that okay? The second one is basically the second conjunction, which handles the case of x is non-negative, y is negative, and the difference is negative. All right? So when we evaluate this logical expression here, when this logical expression, which we call the O or overflow flag, when this whole thing is 1, then we know the sign flag is line. Alright? So between the sign and the overflow, there are 4 possible combinations. And I'm just gonna give you the 4 combinations, and you can tell me what is the true sign in all of those cases. Okay. Okay, so we have the sign flag, the overflow flag, and I'll just say true sign here. Okay. So the sign flag can be 0, the overflow flag can be 0, 0, 1, 1, 0, and 1, 1. Okay. So the first row is saying the sign flag says, okay, is 0, the difference is not negative. And then the O flag says, yep, the sign flag is not lying. So what is the true sign in this case?
0.
0, cool. Okay, that's easy. The second row is a little bit funky because it says, the sign flag says the sign of the difference should be a 0. And then the overflow flag, oh, no, the sign flag is lying. So what do you think is going to be the true sign of the difference? It's going to be a 1. Okay. The third row is saying the sign flag says the sign of the difference should be a 1. And then the overflow said, yep, the sign flag is not lying. What do you think is the true sign in this case?
1.
1. Very good. And then the last row is saying the sign flag is saying the sign of the difference should be a 1. And then the overflow says, no, the sign flag is lying. What would be the true sign of the difference?
0.
0, very good. Haven't we seen this truth table before?
Exclusive or.
Exclusive OR. Okay. So instead of calling the last column true sign, which is kind of ambiguous, I just give it an L flag. I just call it the L flag for less than. Okay, L for less. So the middle end is less than the subtrahend if and only if the exclusive OR between the sign and the overflow is a 1. So now we have a way to tell whether the middle end is less than the subtrahend for signed numbers also. For unsigned values, we use the borrow flag. For signed values, did I say unsigned? For unsigned values, we use the borrow flag. For signed values, we use the so-called L flag, which is the exclusive OR between the sign and the overflow. The overflow itself is its own little expression, which is here. All right? So given all of these things, now we have the mechanism by using subtraction and by introducing this extra O and then the sign of the difference and then the L flag. Now we have the mechanism to know whether the middle end is less than a subtrahend from a subtraction. Okay, which is a great deal. This is really important because this is how all the comparisons and conditions are going to boil down to is one of these 2 flags, the B or the L. Okay? Now, who's going to make use of the borrow flag or the L flag? Well, that we won't talk about until maybe midway through the whole semester. But at this point, what we need to know is there are all of these flags that are computed. Every time you do a subtraction, all of these things are computed. Because subtraction itself does not care whether it's dealing with signed versus unsigned values. It just goes through the motion as bitwise operations. Okay? So when do we really care? It's when we need to make a branch, when we need to make a decision. Oh, we are only supposed to go there if x is less than y. Then we really care, because now we have to decide, are we looking at the B, the borrow flag, or are we looking at the L flag to determine whether we should be there or not? Then we have to make a decision, which flag do we pay attention to? Okay? So our lab activity today is about the stuff that we are just talking about, not the proofs. So relax, we're not going to prove anything in the lab activity today, but we are going to compute the borrow flag, the sign flag, okay, and the overflow flag. Okay, that's what we're going to do in today's lab. All right? I'll see you guys over at the lab. We can take a short break, about 10 minutes. That clock is actually fast. I almost shortchanged you guys.
I mean, you give us a slightly better break.